Well, hello. For this, I want to look at logarithms, which are the inverse of exponential equations. And anytime we see a logarithm, we're really thinking about an exponential equation kind of backwards, or inverse is the proper word. So for example, let's look at these. The log of 1,000, and all of these I could use a calculator, but I don't need one, and so I'm going to explain what these equal without the use of a calculator. So first, all logarithms have a base. If you don't, and the base quite often is shown with a little subscript there of a 2. But look at this first one, I don't see a base, which means it is actually a base of 10. We use log base 10s quite a lot. And so first of all, this is equivalent to log with a subscript 10 of 1,000. So what does this equal, right? Let's say this equals x. Well, what this really means is kind of an exponential expression in reverse. And so this means 10 to the power of, I don't know yet, x equals 1,000. And so anytime I see an logarithmic expression like this, I need to kind of think, okay, what does this mean in terms of an exponential expression? And again, this here, or this here, means really 10 to the power of what equals 1,000? Well, 10 to the power of 3 equals 1,000. Therefore, the log of 1,000 equals 3. And I can kind of do the same idea for all of these. And so for the next one, this means 2 to the power of what equals 16. And so that's what I'm thinking about in my mind. 2 to the power of what equals 16. And once I know what that is, I know what this equals. And so 2 to the power of 4 equals 16. And so the log base 2 of 16 must equal 4. So for the next one, again, I don't see a logarithm of base anything. So this is equivalent to, once again, log base 10 of 1 over 100. And so I need to think about 10 to the power of what, that's what I'm trying to figure out, equals 1 over 100. All right, so for this, I need to remember what negative exponents mean. And 10 to the power of 2 equals 100. Well, I want 1 over 100, and so that's where 10 to the power of negative 2 equals 1 over 100. And so the log base 10 of 1 over 100 equals negative 2. Because again, 10 to the negative 2 is the same as dividing by 10 twice, and we reviewed that last time. Well, another special logarithm that will actually, by the end of this course, work with much more than log base 10 is ln, which stands for the natural logarithm, which is a logarithm of base e. Now, as it says up in the key ideas, e, which may be a new value too, is an irrational number. It's approximately 2.718. But just like pi is approximately 3.14, we are better off just thinking that pi is pi, right? Just like 2 is approximately 1.99, but it's exactly 2. And so while e is approximately 2.718, it's exactly e. And so ln, every time you see ln, or the natural logarithm, that's a logarithm of base e. And as we'll see later in the course, especially in calculus, a base of e is really, really, really helpful to work with. And so this here, I could also write as log base e of e. That's what this means. And so what does this equal? Well, I got to think. Well, this means e to the power of what equals e. Okay, well, that must be a 1. E to the power of 1 equals e. So in the end, this equals 1. And in general, anytime you have a logarithm with what's going inside it is the same base, you'll always equal 1. So in general, you know, if I have log base 2 of 2, that means 2 to what power equals 2? That equals 1. If I have log base 10 of 10, that means 10 to the what power equals 1. So really in general, if I have log base b of b, that's always going to equal 1 in general. All right, so then I have the natural logarithm of 1, which again means log base e of 1, which means e to the power of what equals 1? Well, a power of anything to the power of 0 equals 1. And so therefore the ln of 1, or the natural logarithm of 1, must equal 0. Because again, e to the power of 0 equals 1. And lastly, I have the natural logarithm of e squared, which means, again, log base e of e squared, which means in terms of an exponential expression, e to the power of what equals e to the power of 2. So when you look at it like this, I hope it's clear that that little unknown has to equal 2. And so the natural logarithm of e squared equals just 2. And I can make a generalization about this as well. So in general, anytime you have a logarithm of any base, and then inside it is that same base to some power, I'll just put an x. Last time it was a 2. We'll always get the same idea where, for example, this here means b to what power equals b to the power of x. So it doesn't really matter what this base is. My answer is always going to be x. And so I can generalize this, that this will always just equal x. And quite often when we realize we have a logarithm with an exponential expression inside it of the same base, we can just imagine those canceling each other out. They are inverses of one another. And we'll talk more about inverses later on, but in the end, lots of generalizations, and expect to see the natural logarithm more and more as the course goes on, as well as the base of e, or the number e. All right, here's the other way around. Show that these cannot be evaluated, or if you were to try these on a calculator, you get an error. And so the log of -10 cannot be evaluated. Why? Because this means the log base 10 of -10. Okay, what does that mean? That means 10 to the power of what equals -10? Well, that's not possible. You can't take a positive number, raise it to a power, and get a negative number. And you may be thinking, well, what about -1? But keep in mind, and if you're thinking about that, I would write down this note, 10 to the -1 doesn't equal -10. This equals 1 over 10. There is no way to make the first part work. So the natural logarithm, or the ln, quite often we say when we're feeling lazy, the natural logarithm of 0, this means this means the log base e of 0, which means e to the power of what equals 0. And again, that's not possible. You can't raise a number to any power and get nothing. You can get close to 0, you can't get exactly 0. And again, you may be thinking, what about 0? Well, keep in mind, e, or any non-zero number to the power of 0, equals 1, not 0. And so the last of these, I have log base 1 of 5, which I have to think about. That means 1 to the power of what equals 5? Well, you can't do that. I could repeatedly multiply 1 all I want. I'll never get 5. And again, a common mistake is to think the answer should be 5. But keep in mind, if you just kind of write this down, 1 to the power of 5 equals 1, not 5. And so in general, we don't use logarithms of base 1 for that very reason that anything to the power of 1 equals 1. So in general, we don't use logarithms of base 1. So you'll probably never see a logarithm of base 1 again. Now, logarithms will permeate many parts of this course, but one thing you may be familiar with from science classes or chemistry classes is the idea of pH. And the calculation for pH is, it's a logarithmic calculation, or we say pH is a logarithmic scale. And so the pH is a measure of the concentration of hydrogen ions in moles per liter, and the concentration of hydrogen ions determines its pH with this formula, where pH is minus log of the concentration of pH ions. So what if we know a particular solution has a hydrogen ion concentration with a pH of 3.8? So the question is, okay, we know the pH, what's the hydrogen ion concentration? And so that means I want to take this equation, and instead of pH, I know it's 3.8, which, if you may recall from previous science classes, that means it is an acidic solution, but we don't need to think about that. So I want to solve for H, or H+, the symbol for a hydrogen ion. How do I solve this? Well, I can't immediately think about this in exponential form because of this negative in the front. This is a coefficient of -1. And I need to think of it just a logarithm, not minus logarithm on one side. So I can take care of that easily. I can multiply both sides by -1 or divide both sides by -1, and I get this expression. -3.8 equals the log, and again, base 10, which I don't have to write, of my hydrogen ion concentration. Now I can think about what I've done before. I have just a logarithm on one side, and so in exponential form, what does this mean? Because again, this is in logarithmic form. And any equation in logarithmic form can be written in exponential form, which in this case is the base 10 to the power of whatever the logarithm equals, 3.8, or sorry, negative 3.8. And that what the exponential equation equals is what goes into your exponential, sorry, what your exponential equation equals is what goes into your logarithmic equation, and vice versa. So this is what we're trying to figure out. And this is what we call an exponential form. And quite often it's quite helpful to just go back and forth between these. And with a bit of practice, we can do it quite quickly, as long as we have at some point a logarithm that's been isolated. Notice what I had at first was a logarithm that wasn't quite isolated. There was that -1 coefficient in the front. And at this point, so my answer is 10 to the negative 3.8, which if you decimalize that, we get h plus to be approximately, my calculator tells me 1.58 times 10 to the negative 4. That's in scientific notation, moles per liter, which is great. If I write it in standard notation, recall that means 0.000158 moles per liter. They're both good. They're both the 3 significant figures. And I guess that means we're both done.